Welcome to lecture 24. Today we are going to discuss the Gaussian-like integrals in path integrals and in quantum mechanics and in field theory. So clearly we'll begin with the Gaussian integral defined as I of a equal to integral from minus infinity to plus infinity over x of the integrand is exponential minus half a x square. Okay, and the way we compute this is we take the square of this integral. Here write it a square a, I square a, and integral from over dx and dy from minus infinity to plus infinity of exponential minus half x square plus y square. Now this in the xy direction, there are two separate integrals, but here I can do a change of variables from the Cartesian to the polar coordinates, define r equal to x square plus y square and dx dy is equal to r dr d theta. So I get this thing. And since integrand doesn't depend upon theta, the theta integral comes out to be 2 pi simply. And also we do a change of variable from r square to u. So u is equal to r square. So my exponent becomes exponential minus half a u, and r dr becomes du by 2. And so this 2 and that 2 over here cancels, giving me pi over here. And then when I perform the u integral, then I get this minus 2 by a additional factor, and exponential minus au by 2 is the other part which has to be evaluated at 0 and infinity. And here assumption is made that when I evaluate at infinity, this exponential factor goes to 0, giving me the integrand 2 pi by a. So what I'm assuming over here that the real part of a is greater than 0. And nowhere I have to make an assumption that a has to be real or complex. All I need to know that the real part of a has to be greater than 0 for this to die out to 0 when u goes to infinity. Okay, so that's all I care for. In fact, what people have shown that when imaginary part of a is not equal to 0, then real part of a can be equal to 0 over here for this expression to be valid again. So having I square equal to 2 pi by a, what I get over here is that my Gaussian integral is just square root of 2 pi by a, and assumption is real part of a is greater than 0 over here. Now once I have this integral, I can take a derivative of this integral over here and multiply by minus 2. So when I do this in this particular expression, take a derivative with regard to a, what I get is minus x square by 2 will come out in front, and then I have to perform the integral. But then to cancel the minus half, I multiply by minus 2 over here. So what I am doing is minus 2 d by dA, I act on IA, and that gives me integral of x square exponential minus half ax square, and this is defined to be the mean value of x square. And so this is the definition when I use this derivative under the sign of integral. But if I use the expression of IA here given there and take derivative, then I will get, with minus 2 multiplied, and I get square root of 2 pi by a times 1 over a. The extra factor of 1 over a comes. And when I apply this operator twice on IA, that brings me 2 factors of x square. So that is just expectation value of, or the average value of x power 4. And applying this guy twice on this IA, this expression, taking derivative over here, gives me this expression over here. Okay. Now if I act it n times, then I will have expectation value of x to the power 2n, and the general expression is that will be square root of 2 pi by a, 1 by a to the power n, and this double factorial notation of 2n minus 1. It basically says that it's roughly like factorial, but it doesn't have multiply all the integers, but skips. So 2n minus 1, 2n minus 3, and then so on. It will be multiplied all the way to 1. So that factor comes over here. And clearly, if I take the expectation value of any odd power of x, that will be 0, because odd power of x from x going to minus x is odd, and while the this exponential factor is even, so overall integral is odd, and since the limit is symmetric, this will be 0 for all value of n, where x to the power 2n plus 1 expectation value will be 0. So that is to be expected from the symmetric distribution. Now this is one set of property I have. Now another kind of integral that one is usually interested in is this I of a j. So I just take the same integral but just add in the exponent jx. Okay, and the way to compute this is just complete the square over here. So basically after completing the square, the exponent becomes minus half a x minus j by a whole square, and the only piece that was missing for the completing the square is just added and subtracted. So added piece gives me exponential minus j, exponential j square by 2a factor, which is independent of x, so that can sit outside over here. So here what we did, starting from this initial expression, we completed the square, and then what we did, we shifted the integration variable. So I defined a new variable y, which is x minus j by a, and so dx is equal to so dy will be equal to dx. Jacobian of transformation is 1, so I get this expression over here in terms of shifted variable, and this is just a Gaussian integral. Okay, so that is just square root of 2 pi by a exponential j square by 2a. Okay, so this is what we get here, and now I can say that let me have the expectation value of x in the presence of j. Okay, and that is defined as the integral over dx of x times exponential minus half ax square plus jx. Okay, and this can be written as nothing but d by dj of I aj. Okay, and if I just compute this derivative, I just get square root of 2 pi by a exponential j square by 2a times j by a. Okay, so this j by a would be the expectation value of x, and of course when j is equal to 0, this distribution is nothing but the good old Gaussian distribution, not a shifted one. So there expectation value of j will become 0. So my expectation value that we computed in the previous slide is nothing but what is computed here for j equal to 0, that turns out to be 0. Now second moment under the presence of j will be just the second derivative of iaj with regard to j, and when you compute it, it is just this function with j square by a square term is there, and 1 plus a term is there. Of course when I take j equal to 0 limit over there, I get the previous formula over there. Okay. Now here there is no restriction on j, because even if I change instead of saying plus jx, if had I said minus jx, my prefactor would have been exactly the same, because that just amount to j going to minus j, only the shift would have been opposite direction in this infinite integral. That gives me a result which is independent of j. So whether j is positive or negative, it doesn't matter, because the result depends upon j square. Okay, now another important thing is that in fact j could be any complex number. It could even be pure imaginary, because nowhere I had to make any assumption about j for this integral to be convergent. All I need to know is that the real part of a over here is to be greater than 0. Okay, so if one has an integral where exponent is minus half ax square plus ijx, then all you have to do is replace j with ij in all the previous examples. Okay, and you will have the integrand square root of 2 by a exponential minus j square by 2a, because j going to minus ij, I square created this minus sign. Okay, and here j could be any complex number again. Okay, even when I write it with I, j could be any complex number. Okay? And all I need to know is that confirm the real part of a is greater than or equal to 0. And why equal to 0? Because there is oscillating piece in general when j is not equal to 0. Okay, and imaginary part of a, or the imaginary part of a is not equal to 0. Something oscillating, if it is there, then the real part of a can be equal to 0. Now I can say that my the prefactor of x square is also imaginary. So I just say exponent is half iax square plus ijx. Okay, and when I do that, it amounts to setting a to going to minus ia, and when I do that, this prefactor changes to square root of 2 pi I by a exponential minus I j square by 2a. Wherever you see a, you replace it by minus ia. Okay, and again here j could be any complex number, but the result that we had for a in the previous thing, the real part was supposed to be greater than or equal to 0. Since I'm multiplying a with an I, actually minus I, okay, so the reality now has to be, the positivity has to be imposed on the imaginary part of a. The imaginary part of a has to be greater than or equal to 0 for that integral to converge. So anything, even if 0 imaginary part will be fine as long as the real part of a over here is non-zero, because in this expression real part of a will be the oscillatory guide. Now this results will keep on using. In fact, we have used this this particular expression while proving that action is the quantity that appears in the path integral. When we completed the square and integrated out the momentum in the path integral in the previous lecture, lecture 23, we used this expression because there were a factor of I sitting in front. So this integral was used over there. So all I need to know is that the real part of a is non-zero, and imaginary part should not be negative. That's all, because negative will make it exponential part grow exponentially. Okay. So next thing comes here. It was all using a one variable. Now multivariate Gaussian integrals we consider. So I of capital A is defined as dnx, so n number of variables, of exponential minus half x transpose ax, where x transpose is just this row vector, or x is the column vector, and A is a real positive definite symmetric matrix, so that A transpose is equal to A. Then what I do is that I define another variable y, which is O times x, some orthogonal transformation, such that x transpose ax becomes y transpose O transpose aoy, and this O transpose is also like O inverse, because O transpose O is 1 for the orthogonal matrices. So it basically O inverse AO, so that's like a symmetry transformation, and I assume that or rather I choose a symmetry transformation that diagonalizes this matrix A to dA, okay, where dA is written as, or diagonal entries are just lambdas, with all lambda i's greater than 0 for all I. Okay, so and under this transformation dny will be just determinant of O dnx, and determinant of O is 1, so it will be invariant, the measure is invariant. So IA just becomes dny exponential minus I yi square lambda I, sum over I is there, and so it is a bunch of independent Gaussian after doing the rotation, and that basically becomes, the result is I equal to 1 to n square root of 2 pi by lambda I. Okay, and the product of lambda I is nothing but the determinant of A, because determinant of any matrix is the product of all its eigenvalues, which is when diagonalized is the product of all the diagonal entries. So final result is the square root of 2 pi to the power n divided by the determinant of A. So this result is proportional to negative half power of determinant of A. That's what is the result. Okay, now here again I can do a shift in the integral. So the integrand is half minus half x transpose ax, and I just put j transpose x over there. So my initial factor will remain same, and additional factor, which is used to be j square, will become exponential half j transpose A inverse j. And the way to show it, that you define y is equal to x minus A inverse j. Okay, so y transpose would be x transpose minus j transpose A inverse transpose, which is nothing but A inverse, because A is a symmetric matrix. Okay, and then when I write y transpose AY, I expand this, and these two terms, which is j transpose x, which is a number, and x transpose j, which is also a number, and these two numbers are equal, because if I take transpose of a number, it's a number itself. So x transpose j whole transpose is the x transpose j itself, because this is just a number. But if I use the property of matrices, then it is just this guy. Okay, so these two guys are basically the same, so they just add up. Okay, so what you have is y transpose ay is x transpose ax minus twice j transpose x plus j transpose a inverse j. Okay, so because this last piece, you have one a over here, so one of the a inverses cancel, so you have j transpose a inverse j. This is what sits over here if you put in all the factors properly. Okay, so n-dimensional integral also we can compute in this manner. Now again, I'm just repeating this line over here. So minus half x transpose ax plus j transpose x was this integral 2 pi to the power n by determinant a square root of this and exponential half j transpose a inverse j. And here assumption is that real part of all the eigenvalues is greater than or equal to 0, and the imaged part is not equal to 0. So well, imaged part not equal to 0 is not a required condition. If imaged part is equal to 0, then lambda I has to be strictly equal to, it is strictly greater than 0. Equality is not allowed. Now I make a change. Okay, and again here ji can be any complex number. Entries of j could be any complex number. Now here j is replaced by ij. Okay, and all it changes is the sign over here in the exponent. Now apart from that, if I also change a into, going to minus ia, okay, then that changes a over here in the inverse, and the expression becomes minus I by 2 j transpose a inverse j. And here again the condition is that j could be anything, but imaginary part of lambda I has to be greater than or equal to 0. So my A matrix has to have that property. Okay, the imaginary part of the eigenvalues has to be positive. Now for here I was talking about j and x to be multi-component vector. So when I go from so we started with the single variable, that's like a single coordinate, and when I went to multiple variable, it's like multi-particle in the same coordinate or one particle in multiple dimension, whichever way you want to interpret it. There are countably many degrees of freedom x, so that's why d and x, n number of independent coordinate. Now when I go to quantum field theory, then the change that happens, that phi of x is a coordinate and x is just a label. Here xi, I is being the label, here phi of x, x being the label, and x is continuous. So the corresponding Gaussian integral that will be there is that integral of all possible value of phi of x, because phi of x is a variable, and exponential of d4x. The d4x acts as much like the summation of I. Okay, so phi of x multiplied by some a operator acting on phi of x. So this is a counterpart of this guy, that a acting on x is another vector and a transpose is another vector, so you just do a dot product. So here a acting on phi is a vector and phi is a vector, you do a kind of dot product, and d4x simply says sum over all possible value of x. Okay. And same way jx phi x. Now I'm not writing this corresponding guy of this functional determinant part. I'm interested in this thing because this is what is going to be used mostly in various studies. Okay, so I'll just say that this particular integral is proportional to exponential half dx dy j of y dx minus y j of x. Okay, it's a double integral because here two indices are summed over, a inverse being a matrix. Now what is this d is that if a, the operator a, acts on d of xy, that gives me delta for x minus y. Okay, this is like a delta function is a counterpart of identity matrix. So basically d is nothing but inverse of a, which we are looking over here, which earlier we found. So this d is what you usually call the propagator in this field theoretic setup. Okay, so here I'm making a jump from a countable number of degrees of freedom, uncountable number of degrees of freedom, and the prefactor I'm not writing explicitly. Okay, so this integrals would work like that. And of course, if j goes to ij, then this will change its sign, and if a goes to minus ia, then it will change sign further. Okay, and then people sometimes use a convention where the I sits on the right hand side, or like I times d is the inverse of a, or other minus I times d is the inverse of a is what the convention is. So accordingly, this d that will sit in later lectures would be different from what is there in this particular expression. Now, this various integrals that we have been talking about, we also have to make sense that the real part or imaginary part that were greater and not greater. So for that, for the pure real stuff, there is a method called method of steepest descent, which is usually used in the statistical mechanics also, as I mentioned while discussing the path integrals. So the similarity between path integrals and the statistical mechanics is that in statistical mechanics, weight factor is always exponential minus beta h some energy. So here energy minimization comes out to be the rule of thumb. And for the case of path integral is the phase stationary phase method. So there is a method called steepest descent, and using this we basically compute this integral from minus infinity to plus infinity dx exponential minus beta of f of x times g of x. Now beta is a large number. That's what is we use. So for large beta, what happens? Small variation on fx make this guy change, exponential guy change very much. Okay, so it can decay very fast. So this particular integral is written as sum over x naught, where x naught are the points where f has a local minima. Okay, and then exponential minus beta f of x naught, g of x naught, and then this extra factor is there. So let's just try to prove this, how to sum over all possible minimas, that is the x is being the stationary point and the minima of f of x. So in general we can write f of x when it is near the stationary point to be f of x naught plus half of second derivative x minus x naught. First derivative is 0 for it to be the stationary point. Okay, and the second derivative has to be greater than 0 for it to be a minimum. Now if I write exponential minus beta of f of x, then I can just write exponential minus beta of f of x naught, and the next piece will be exponential minus beta by 2 second derivative of f of second derivative of f at x naught, and then x minus x naught. Okay, now if I'm moving x close to x naught such that x minus x naught square is less than or similar to 1 over beta f double prime. Remember, beta is a large number I'm looking for. In fact, beta times f could be f double prime, could be the large number together. And under this is approximation of this function, exponential function over there. And if I do a integral over that narrow range and g of x is not changing over this narrow range delta, then basically it's a constant, and constant equal to g of x naught, so that comes out. Okay, and this factor is a constant that sits over here, and rest of the thing is just ordinary Gaussian integral, so that will give me this factor. Okay, so for near one of the extrema or minima, I get this function, and this is demonstrated over here. Let's just say f of x, instead of having single minima, has many minima, and I'm choosing a function f of x to be like that, and I chose sine pi x. So it has minima at all these values. Okay, so x equal to 1.5, 2.5, 3.5, and so on, and also negative side minus 0.5, then this is minus 0.2, and so on. Every one step it will be like, okay, this is 1.5 and then this is 2.5. Is it 1.5? I think this is already 4. Oh yeah, 3.5. So anyway, so it has several minima, and corresponding to each minima, okay, this guy will be large. Okay, so this is the multiple spike function is the function that we are trying to integrate out. Integration means that what is the area under that curve? The area under that curve would be the value of the height times the width. The height is given by the g of x, okay, and width is kind of given by this square root of 2 pi by beta f double prime. So this kind of gives the width. So this is the area, and this is another scaling factor comes because this at minima the function has some value, right? So happen for the plot that that we have chosen, it has minima at every n plus 3/2 by 2. So for every n integers, maybe 2n I should have written, and f the minima f of 0 is -1 for all the minima. So my overall factor is kind of a constant, okay, and it's same for everybody, so I can scale up, and so this factor turns out to be just exponential beta, and I have taken beta to be 20 pi for these plots, okay. And while plotting, I have divided this spiky thing with 10 power 27 numbers such that it becomes comparable, and this red curve is just the slowly varying function g of x, okay. So you can see that the exponent, the number of minima it has, it basically samples from only those minimas. The value of this g of x only add those minima that appears in the sum, okay, because when beta is very large, this Gaussian basically becomes delta function, and you get that value of g of x only at that point. Okay. So this is the method of steepest descent, and in terms of statistical mechanics, what it means that wherever energy is minima, only that guy will contribute. Here we have chosen a function which has many minimas, but ideally, you know, Hamiltonians and all these things, system usually have one minima, okay. And in case if there is a function, if there's a system which has several minima with different configuration, okay, then all of them would contribute, much like here, okay. That's why sum over all minima is there. Now next comes when the exponent is imaginary, and we use the method of stationary phase. So my integral to be used is dx exponential I beta f of x times gx. Only thing is changed is I times, and the answer is again same. The exponential I beta of f of x naught is there, and it is g of x naught that appears over there with this factor, because this I beta over there, here's the additional factor of I is there, okay. Now for plotting, what I did, I took the real and imaginary part of this function exponential minus I beta x. So I took cos beta of f of x times g of x that I plotted over here, and wherever the exponent is stationary, okay, not minima, just stationary. So you see here it is maxima, the g of x, sorry, f of x is maxima. So you can see less fluctuation. Here it is minima, so it's less fluctuation. Here maxima and less fluctuation. So all the extrema will contribute, okay. So here x naught is not just a minima or maxima, it's just every extremum point over there. And why I writing over there that for the extremum point, either it could be maxima or minima, so the f double prime could be either positive or negative. So it's nice to write this thing in terms of sign of f double prime, okay. So this I by this guy simply becomes this guy over here, and so basically I have either plus I or minus I, which is usually written in this form in various steps. What happens is, the most of the physics application, we usually have exponent with only one stationary point. Here I'm, for demonstration purposes, I'm showing many. So we will have contribution from one place only. However, there are some systems with non-trivial topology that can have action to be extremum at countably many configurations, okay. And that countably many could be countably infinite also, okay. But as I said, that here these are the functions that I'm showing. They are very nice function, because both here maxima and minima are of order 1, right. Maxima is at 1, minima is at 1. So in both the cases when I write f of x to be either plus or minus 1, so this exponential plus or minus I beta would appear. Okay, that's a pure phase that is appearing over there in this expression, and they are same phases both the places. Okay, so they are not changing much. Only thing that is changing is just g of x. Okay, so if we have a system where g of x is non-trivial, or this value of maxima at all the maxima is different, or the value of the function at extrema is different, very different extrema, then they will contribute differently, and hence in the final result they will contribute differently. Here the example is very simplified because f of x is nothing but sine of x. I just use the same example with beta going to minus beta was replaced by I beta, that's all. So with this I conclude this lecture, and basically this is an example of various mathematics, and this plots, I don't know if you find it anywhere, I plotted it for this particular lectures to show that how under this situation the Gaussian integral basically acts like delta functions and picks up the values over there. Okay, and here the contribution away from this central piece dies out exponentially, but in the case of stationary phase method, the contribution from neighboring from the anything other than the extrema point, it dies out algebraically. Okay, so it will be x minus x naught power something, with that it will die out, while for the steepest descent case, for the real exponent case, it will die out with exponential minus some number times x minus x naught power something. Okay, so it will die out exponential over there, and here only algebraically. So this is just a demonstration over here. This is for the real part and the imaginary part, and you have to keep the signs, all these things put together to find what is the integral over here. I did not do putting all the pieces together, just showing the real and imaginary part separately. And the fact that whether it is I put so imaginary part means I do, instead of exponential I have sine x. Okay, sine of whatever is the exponent. So the purpose was here only to show that how stationary phase method works. So wherever this function is oscillating very, very fast, the basically area under that curve is 0, because the positive movement and the negative movement have roughly the same areas, roughly, not exactly, and they kind of cancel out. Right? And if you increase beta, that cancellation is more and more accurate. Much like if you increase beta over here, this delta function is more and more sharp. Right? So with this I conclude here, and we'll meet in next lecture where we show using various Gaussian integrals that how come a path integral, which is just an integral like Gaussian integrals, a bunch of Gaussian or modified Gaussian integrals, how that can be related to something like quantum operators, and the time, operators have to maintain orders, time order and all these things there. How does that make sense in this picture is what we are going to see in the next lecture.